Now we're going to start talking about the momentum equations. So the momentum equations are going to be what determines how fast things are moving. And there are two types of ways to look at the momentum equations in fluid mechanics. There's Lagrangian and Eulerian. Lagrangian is named after Lagrange, and Eulerian is named after Euler. The difference between Lagrangian and Eulerian is that Lagrange tries to follow an individual fluid packet. So imagine a small bit of fluid here of size delta x, delta y, and delta z, and that little box of fluid is moving, potentially, if it gets pushed by some force. And in Lagrangian fluid mechanics, we actually try to follow that box of fluid. But that's hard to do because all the fluid looks the same. So it's not that it's hard to calculate how fast the fluid box will move, that we can do, but it's hard to see where it went. It's going to go somewhere else. We're not going to really know how to tell this box of fluid from some other boxes of fluid. They all mix anyway. So it's not realistic in most circumstances to think about a packet of fluid staying together. Eulerian fluid mechanics studies instead the geometric position and the fluid that flows through it. So we're going to mostly use Eulerian fluid mechanics in this class, but there are applications of Lagrangian fluid mechanics, particularly when you're dealing with small droplets or interfaces. We're going to start by looking at the forces that you would have if you just had this packet of fluid and you wanted to think of it in a Lagrangian way. It's a little easier to see the forces. So the three types of forces you're going to have are pressure, viscous, and body forces. And we're basically just going to use F equals ma to create an equation using those forces. So we're going to figure out all the forces and then relate that to mass and acceleration. So the first force we might have, if we're looking at the x direction, the x momentum equation here, is the pressure forces. So the pressure forces are going to act only normal to the direction of the surfaces. So the pressure forces are only going to push in the x direction at the position x and x plus delta x. Now the surface at x, you can't really see it. It's the back of the box. But the size of that surface is delta y and delta z. And since it's pushing from the back, it's going to push the box forward in the positive x direction. The surface at x plus delta x is the one I've shaded right here. So that surface, the pressure is going to push the box the other way. So it's going to push it negatively, which is why we have the negative sign. It's the pressure at x plus delta x, and it also has an area, surface area, of delta y and delta z, as you can see there. Here's a viscous force. So this viscous force is caused by faster moving fluid that's adjacent to our box, dragging our box either forward or backwards. So if du dy is positive, that means that our box has a higher velocity than boxes that are just to the left of this box in the lower y regime. So if there's slower moving fluid next to our box, that's going to cause our box to slow down. So if du dy is positive at the surface of y, which is this surface here, that's going to cause our box to slow down as it tries to slide by a slower moving box of fluid. And the area of that interaction is delta x times delta z, the surface area of that surface. Similarly, if du dy is positive over here, it means that fluid just to that side of our box on this side is moving faster than our fluid is moving. And that's going to tend to drag our box forward and exert a positive force. And again, the size of that surface is delta x, delta z. Exactly identically in terms of conceptual understanding, if there's fluid below our box that is slower in the z direction, that would be below us, then that's going to drag our box backwards. And if du dz is positive, that means our box is moving faster than the box right below us. And similarly, and that's also, acting on a surface that has a size delta y, delta x. And similarly, you have mu times du dz again to represent the surface at z plus delta z. So that would be this surface up here at z plus delta z. And if the fluid above us is moving faster than our box is moving, du dz will be positive, and that will tend to pull our box forward as a faster moving bit of fluid slides across the top and pulls our little bit forward. And you can do the same thing in all the viscous directions. So we're going to have mu, I won't go over each one with this one, but du dx at x, which is going to be on a surface delta y, delta z, and then you're going to have a positive mu du dx at x plus delta x, and again delta y and delta z. And there's no body force in the x direction, right? No body. Usually body force is not in x. Body force is going to be like gravity. So we'll put our gravity in the z direction as we usually do. Sometimes it's in y. It's almost never in x. We just don't define our coordinates that way usually. So we're going to set all these forces and we're going to equal to m and then the acceleration in x, right? So that's going to be max. We know that max can be rewritten because we want to put things in terms of velocities. So the x acceleration can be rewritten as du dt. So we're going to, and we know how to calculate mass. We've done this before as well using variables we like in fluids. So it's rho, delta x, delta y, and delta z, because delta x, delta y, delta z, that's the volume of our little box. So we have volume times density gives us a mass. So we put all that together, and we say rho, delta x, delta y, delta z, times du dt is equal to all of these forces that we just listed in length. So they're all equal to that. Now I'm going to divide everything by delta x, delta y, and delta z, right? So I'm going to divide everything by delta x, delta y, and delta z. So if you look back at these terms, this one has a delta y and delta z in it. This one has a delta y and delta z in it. This one has a delta y and delta x in it. This one's supposed to have a delta y and delta x in it too. It just forgot. This one has a delta y and delta z, delta y and delta z. So they all have 2, but none of them have all 3. So every one of them is going to end up being divided by the one they don't have. So we're on the left-hand side, we're going to have rho du dt, because I've divided everything by delta x, delta y, and delta z. And on the right-hand side, I'm going to have things like this. P at x plus delta x minus p at x divided by the one that didn't have, which is delta x. The next one, I have mu du dy evaluated at y plus delta y minus u du dy at y divided by delta y, because that's the one that it didn't have. Then I have mu du dz at z plus delta z minus mu du dz at z divided by delta z. And I have mu du dx at x plus delta x minus mu du dx at x, all divided by delta x. Hopefully you recognize all of these as we've done before now. These look an awful lot like derivatives because they are. So we're going to take all of these things and we're going to take the limit as delta x, delta y, delta z goes to 0. And when we do that limit, these are all going to turn into derivatives. So we'll write this nice and cleanly on the next page. When we do that, we have rho du dt on the left. That's what we had before. Then we're going to have the derivative of p with respect to x, because that's what that term was. Then we have to decide, if you look at these terms, this is the derivative of mu du dy. But if mu is constant, and we usually treat it as constant, we can take that mu out, and they all had mu. So it looks like this: d squared u dy squared plus d squared u dz squared plus d squared u dx squared. That is all of those. This is assuming mu is constant. If mu is constant, we can do that. And we have two types of forces. We have pressure forces. And here we have viscous forces. And if we had body forces, then we would have another term, but we don't. So that's the equation to find acceleration in Lagrangian mechanics. So this is the Lagrangian x momentum equation. And we're going to have to do more with that in order to change it into Eulerian fluid mechanics, which we're going to want to do. Because as I said, this works if you're going to track an individual packet of fluid and follow it around, but it's very hard to track a little individual packet of air to see where it goes. So we're not going to do it that way in the future.